This is my fifth nuclear physics video, a bit more about decay, particularly about beta decay. Now, in all interactions, there are a number of quantities which are always conserved. Momentum, mass stroke energy. Later on, we'll see that mass and energy can change into each other. But mass stroke energy, the total, is conserved. Charge is always conserved. Lepton number is conserved, and boson number is conserved. Let's look at a couple of interactions. Firstly, the decay of oxygen 15. So oxygen 15 decays into nitrogen 15 plus a beta plus a neutrino. Now, what's happening inside the nucleus is that a proton is changing into a neutron. From the video on quarks, you might figure out that what's happening is that an up quark is flipping and becoming a down quark. But these other two particles, we've got this thing called a positron. Now, a positron is the antiparticle of the electron, and it has a lepton number of -1. An electron has a lepton number of +1. It's a particle, but this positron has a lepton number of -1. It has to be created so that the total lepton number stays the same. Well, we also have this neutrino, and a neutrino has a lepton number of +1. So we're creating a particle and an antiparticle, so our lepton number stays the same. What on earth are neutrinos? Neutrinos, the word neutrino, it's little neutral particle. They have almost no mass. They travel at almost the speed of light. Their existence was proposed by Linus Pauling to justify the missing kinetic energy in beta decay. If you look at the diagram there, there's beta decay happens, the beta particle is chucked off, the nucleus recoils, but then there's missing energy. So it was suggested there must be another almost undetectable particle involved. The chances of detecting a neutrino are very, very small, because the chances of them interacting are so small, basically because they are neutral. The sun emits a ridiculously huge number of neutrinos every second because they're produced in the reactions that happen inside the sun. And if you imagine holding up your thumb, every second 60 billion solar neutrinos go through your thumbnail, and that's a lot, and you don't know about them. Positrons, a little bit more about positrons. A positron is an antiparticle, and they don't exist for very long because basically if matter and antimatter get together, then they annihilate each other. And so this poor little positron, which has just been emitted, pretty soon it's going to bang into an electron and they're going to annihilate each other and produce a couple of photons, gamma photons. This is used in positron emission tomography. The patient is injected with glucose containing oxygen 15. This accumulates at tumours because there's a lot of respiration happening in a tumour. This decays and it produces positrons. The positrons are almost immediately annihilated when they bang into electrons, and this produces two gamma photons, and we can detect the gamma photons, and from the difference in time that they are detected, we can figure out their location. The patient is put in this big machine, looks a bit like an MRI scanner, and the body is scanned in slices, hence tomography. Remember, tomos means slice, and you get images, slices of their brain. It can all be put together as a kind of a 3D thing as well. Consider the decay now of carbon-14. Now, carbon-14, a very important decay in carbon dating. This decays into nitrogen-14 and a beta minus and an antineutrino. So what's happening inside the nucleus is that a neutron has changed into a proton. A down quark has flipped and become an up quark. These other two particles, the antineutrino, we're creating an antiparticle because we're also creating a particle, and so conservation of lepton number, we must also create an antiparticle, an antineutrino. Could you have a go at this question now? Pause the video, very common little question. And the answer is that 0.51 mega electron volts. Back to this graph, I have mentioned it before and we will come back to it later as well. It's a graph of N against Z, neutron number against proton number. The sausage in the middle is all of your isotopes. In the middle of the sausage is the stable isotopes, and then there are isotopes above it and isotopes below it. The ones above it are ones which have too many neutrons to be stable. So above the line of stability is all your beta minus emitters. Below is these isotopes have too many protons to be stable, so they're going to be beta plus emitters. Your alpha emitters tend to be higher up the sausage. If you want to lose weight, a good way of losing weight is to give off some alpha particles. And then there's some fissile isotopes up there as well. We'll talk about them later. So this graph shows all of the isotopes. In the middle is our line of stability. To the left are beta minus emitters. To the right are beta plus emitters. The graph below the text here is looking a bit closer. If you give off a beta plus particle, then you are basically losing a proton, gaining a neutron, so it's a move kind of diagonally top left. If you give off a beta minus, then you are losing a neutron and gaining a proton, so that's kind of down right. And then if you give off an alpha particle, you're losing 2 neutrons and 2 protons, so that's a big move down left.